looked up at the sky and wondered how tons of metal can defy gravity and stay airborne? It seems almost magical, doesn't it? But there's no magic involved. Just pure, fascinating physics at work. In this video, we're going to unravel the mysteries of flight and explore exactly how airplanes manage to stay up in the air. We'll break down the complex concepts into easy-to-understand explanations, so you don't need to be a rocket scientist to follow along. Get ready to discover the forces that lift airplanes, the crucial role of wing shape, and the ingenious ways engineers have harnessed these principles to create the incredible machines we see soaring overhead every day. By the end of this, you'll have a solid understanding of the amazing physics that makes flight possible. Let's dive in. The dream of flight is as old as humanity itself. We've looked at the birds soaring effortlessly and yearned to join them. But turning that dream into reality took centuries of ingenuity, experimentation, and a healthy dose of failure. Early ideas, like flapping wings powered by human muscle, proved impractical. Thinkers like Leonardo da Vinci, though, sketched out designs and theories centuries ahead of their time. He envisioned ornithopters and even preliminary concepts of the helicopter, laying the groundwork for future inventors to build upon. The 18th and 19th centuries saw crucial advances in understanding aerodynamics. Figures like Sir George Cayley are considered fathers of aviation. Cayley identified the fundamental principles of lift, drag, and thrust, and he even designed and built gliders that successfully flew. He recognized that a fixed wing, rather than flapping wings, was the key to sustained flight. Then came the Wright brothers, Wilbur and Orville. They weren't just inventors. They were methodical experimenters. They built wind tunnels, carefully studying how different wing shapes generated lift. They realized the importance of control, developing a system of wing warping to allow the pilot to steer and maintain balance. Their meticulous approach culminated in the first successful sustained, controlled, heavier-than-air-powered flight at Kitty Hawk, North Carolina, in 1903. But the story doesn't end there. The Wright brothers' success sparked a global race to improve and refine aircraft. Engineers and inventors across the world built on their work, developing more powerful engines, stronger materials, and more sophisticated control systems. Aviation quickly evolved from a daring experiment to a practical means of transportation, forever changing the world. So, how is this physics of flight stuff actually used today? And what difference does it really make? Well, practically every aspect of modern aviation, from the design of aircraft wings to the routes they fly, relies heavily on the principles we've discussed. Think about it. Engineers use computational fluid dynamics, or CFD, which is basically super-powered computer simulations, to model airflow around a plane. This allows them to optimize wing shapes, reduce drag, and improve fuel efficiency. That means more range, less pollution, and cheaper flights for you. Beyond commercial airliners, understanding these concepts is crucial for military aircraft design, allowing for faster, more agile, and stealthier planes. And it's not just about planes. Wind turbines, for example, use airfoil shapes very similar to wings to capture wind energy efficiently. The impact on society is enormous. Air travel connects the world, enabling global trade, tourism, and cultural exchange. We can hop across continents in hours, delivering goods, services, and people faster than ever before. This interconnectedness fuels economic growth and fosters understanding between different cultures. Think about disaster relief. When earthquakes or hurricanes strike, airplanes are often the first responders, delivering essential supplies and personnel to affected areas. Helicopters, using lift principles, can reach remote areas inaccessible by other means. And of course, there's space exploration. The principles of aerodynamics, while less dominant in the vacuum of space, still play a vital role during launch and re-entry, shaping the design of rockets and spacecraft. Without a firm grasp of the physics of flight, we wouldn't be exploring the cosmos. From everyday travel to groundbreaking scientific advancements, the physics of flight underpins so much of our modern world. So, let's quickly recap. We've seen how lift, generated by that cleverly shaped wing and the power of the engines, overcomes gravity. We explored the dance between thrust and drag, the forces that propel and resist the aircraft. And we uncovered how controlling these forces, through the flaps, ailerons, rudder, and elevators, allows pilots to navigate the skies with precision. The physics of flight is a constantly evolving field. We're already seeing innovations like blended wing bodies and electric propulsion systems pushing the boundaries of what's possible. Perhaps one day, we'll even see commercially viable hypersonic passenger jets effortlessly soaring across the globe in a matter of hours. Who knows what the future holds? If you enjoyed this deep dive into the forces that keep airplanes up, please hit that like button. And don't forget to subscribe for more exciting explanations of the science all around us. We've got plenty more fascinating topics lined up, so stick around.